Welcome to this one of the three AI panels that we're going to have during this event, the ICM 2026. And this first one is Mathematics for AI. And I just want to remind you that the next panel is AI for Mathematics. It's going to happen tomorrow, 3 to 5 in this big room. And the third one, AI for college mathematics, which is more dedicated to education, is going to happen on Monday, 5 to 6:30 p.m. So now that I reminded you of the three events, I would like to introduce our panelists. I would like to thank them for agreeing to be part of this panel and to give us a lot of their wisdom in AI mathematics for AI. So I'm going to start with Randall Balestriero. Randall is an assistant professor of computer science at the Brown University and part-time researcher at Meta. Professor Balestriero is an AI researcher building the theoretical foundation of world models, self-supervised learning, and learnable signal processing for the time series. So maybe raise the hand who is that's Randall. And let me just say that each one of them will give a presentation of about 15 minutes, and you will have a chance to ask each one of them questions after the presentation. So that's Randall. Then we have Peter Bartlett. Peter is professor in the Department of Electronic Engineering and Computer Science and the Department of Statistics and head of the Google Research Australia. Since 2020, he has been director of the foundations at the Data Science Institute, a director at the Collaboration on the Theoretical Foundation of Deep Learning. His research interests include machine learning and statistical learning theory, and a lot more. Then we have Joan Bruna. Joan is professor of computer science, data science, and mathematics at the Courant Institute and Center for Data Science at NYU. Professor Bruna's research touches several areas of machine learning, signal processing, and high-dimensional statistics. He is particularly interested in the mathematical foundation of machine learning, covering optimization, representation, and statistical aspects of their interplay. And finally, Bin Yu. She is the CDSS Chancellor Distinguished Professor of Statistics and Electrical Engineering and Computer Science and Center for Computational Biology at the University of California, Berkeley. Professor Bin Yu leads the U Group at UC Berkeley, an interdisciplinary team in statistics and the EECS, dedicated to advancing machine learning, artificial intelligence, and veridical data science. She's going to tell us more about that. So without further ado, I will say that we can start with the presentation, and the first person to speak is going to be Joan. Please.
Okay, thank you very much. Thank you, Gigliola. And I'm honored to be representing my research community on trying to tell you a little bit about how mathematics can be used to understand several aspects of AI, and also an effort to try to put all these pieces together. So AI systems today, I guess you have been using them. They are very complex, they are very hard to define, and they are also quickly evolving. A little bit maybe like a complex living organism or maybe a complex material. And I guess the point of my talk today is maybe to convince you that there are several interesting mathematics that appear once one chooses the right level of abstraction, right? And there are several levels in which one can view this system, right? Similarly as materials, etc. So to make this point, in today's talk, I'm going to just do like a very broad tour and like an overview focusing on maybe 4 representative levels, covering maybe what we call feature learning on very stylized models. Then we're going to discuss mean-field limits of neural networks. Then I'm going to discuss generative models using ideas from transport measure. And finally, I'm going to say a few words about reasoning, which is, I guess, something that we all care about here. Okay, so the modern AI, the modern paradigm in which we do machine learning today is based on this premise of pre-training and then fine-tuning. And in very simplistic terms, pre-training, we have to learn a function using a lot of examples that is not the function that we care about, right? We care about, at the end of the day, we care about the different function f star, okay? And so first question is, in what sense training a auxiliary function can help me train better the function I care about? And in some sense, the natural answer is to think about composition, to approximate functions by composition, right? And in some sense, if we try to approximate this pre-training function as a composition, maybe one of the first factors, the first factor here written as psi, can be used, can be recycled to hopefully like reduce dimensionality and learn the second function that the one care about more efficiently. And this, I would argue, that is really the defining characteristic of neural nets, right? This ability to learn compositions is something that you don't have in kernel methods, for example. And so natural question is, can we understand mathematically this phenomenon of feature learning, maybe in some simplified model, something that we control a bit better? And over the recent years, my community has, in some sense, built a pretty good understanding of one such success story that we call these multi-index models. And in this model, everything is controlled. So we have inputs, covariates that are Gaussian, and the responses are generated by the input by just projecting the input on a secret low-dimensional subspace, right? And in some sense, the features in this model correspond to really understanding and capturing this relevant information, right? That is this low-rank matrix. And so there are a few things that I want to talk about that we know about this model, but I'm just going to here emphasize a couple of important aspects. First is that shallow neural networks not only are efficient at learning this model, in some sense they are as efficient as a broad class of polynomial time algorithms. But we have a good understanding of optimality on this problem, meaning that the number of samples that we need to observe is something that we control pretty well. And then the other aspect that is interesting in this model is that the way the information, these features are learned, happens in a very interesting, progressive, or if you want, sequential manner, right? There's an incremental learning, the same way that when you learn a complicated task, first you learn kind of the simple part of the function, and then once you have learned the simple part of the function, you can learn the next complicated part of the function. And in this example, because everything is under control, we understand these subspaces by using harmonic analysis. So we have a good understanding of this sequential learning objective. So now that we understand this, simplified toy setting, the natural question is, what about more complicated problems, right? Where this, Gaussian structure is not there. And so this brings me to the next resolution, if you want, that is given by, in this example, this mean field limit, right? So if we stay with this shallow neural network, which already captures the main difficulty of this problem, which in this case, we have a complicated optimization problem because this function is nonlinear. And so because this network has invariance to permutation, all the neurons basically are the same, you can view this system as an interaction particle system, okay? And so an important perspective was brought by a number of works where instead of viewing the problem from the original parameters, now we can describe this object through the empirical measure, okay? And so once we have this empirical measure, we can then take the number of particles to infinity and describe this object through just a standard smooth probability distribution. And so in this example, the dynamics, the learning dynamics are expressed by a PDE, which is like a transport equation, and in which we understand, like the community understood several aspects about convergence, local convergence, and some notion of qualitative global convergence. So natural question is, now that we understand, these dynamics in this ideal setting, can you bring these guarantees back to the original model, right? The actual neural net. And so for this, there's an advantage. This is still an active area of research. One program to do that is first to sharpen, to understand better, to get kind of quantitative global convergence guarantees in time, and then to try to bring the guarantees that we have in the mean field limit back to the finite network. And this involves controlling the fluctuations that come from discretization. And this is a topic that is in some sense familiar to probability theory and kinetic theory, that is referred as this propagation of chaos. And another interesting direction of the field is to bring this program beyond the shallow neural network to more complicated architectures, such as transformers. And Philippe Rigolet is going to give a presentation on this topic, I believe, in 2 days, on Monday. All right. And now let me move yet another level of abstraction and talk about generative model, right? Like this problem of now I have some complicated high-dimensional distribution. Here, for example, I have a bunch of buildings from Barcelona, my hometown. And to generate this data, what we are going to do is to try to view this complicated distribution as a deformation of some simpler distribution that we can control, for example, Gaussian. And for that, the first thing that we do is we build an interpolation between the complicated distribution and the simple one. And we interpolate by just averaging the samples, as you see here. Okay. And once we have this interpolation, we again rely on this duality that we already saw before of just writing this relationship through in Lagrangian form, and so building a transport equation that explains this interpolation path. And once we have this transport map, now we can use it to produce novel samples by just following the characteristics with this transport map. And this is something that we can do by just black box the problem. We can just obtain this drift by just fitting an arbitrary neural network using available samples. And this can be done using standard regression objectives. So the kind of representative questions in this field obviously correspond, just to give you a certain taste, for example, can be seen, what are the transports that we can learn efficiently? Can we use this technology to sample from other distributions except from this base, for example, for posterior inference? And this is a technology that is currently being explored very actively in scientific applications, for example, in biology or in fluid dynamics, etc. And there are also a number of talks in this conference that go deeper into the connections between different areas, such as PDEs, optimal transport, and stochastic localization by Gabriel, Enrique, and Nima. All right. And then let me just kind of finish this kind of tour by talking about reasoning. And in some sense, what I'm arguing is that if we really want to build some mathematical understanding of this new paradigm of using AI to solve math, in some sense, thinking in terms of a trained prediction is no longer sufficient, right? If you typically you think about machine learning as a problem where the more I put resources on training, the better it gets. But these days, these models introduce a different axis of improvement. That is how much compute I allow this model to use during test time. Okay, and this is something that doesn't fit into the framework of statistical learning. And so, in some sense, the right way to think about this new field is to go one level abstraction, one level up in the abstraction, and to think in what we call these harnesses, right? Where now it's a kind of interactive, iterative environment where the LLM is just one component that interacts with many other things, for example, verification, or planning, or formalization, etc. And to give you also a hint of what are the representative questions in this area, these are obviously a bit more speculative. This area is much more still work in progress. Network interesting questions emerge. For example, what is the right way to interface between kind of the probabilistic thinking that comes from LLM and the verification that comes from these formalization steps? Or going back to my initial snippet, what are the features that are relevant in this problem, right? Before we use the stylized model to understand very well what are these intermediate kind of stepping stones. What are the associated features, right? And what are the leaps that actually are associated with these reasoning problems? So to summarize, what I try to convey here is that if one looks at these big, messy AI systems at different kind of levels of abstraction, there are different things that appear, right? And at each level, my point, I guess, is that there's no right level, right? There's interesting mathematics and interesting questions and a lot of activity in each of these levels. And so with that, I would like to thank you for your attention, and special thanks to Emmanuel, Philippe, and Margalit for helping me prepare this presentation. Thank you.
Thank you. And I want to remind everybody, if you have a question, just write it for yourself. And then at the end, when everybody presented, you can come up one of the microphones that will be available and ask your question. Peter, you're next.
All right.
Great.
So very happy to be here. I wanted to focus on a couple of different directions, I guess. The first is about the science of machine learning and AI. So, you know, a lot of what Joan talked about there is really in this direction. And this is understanding these systems, modeling these systems in the same way in applied math we might model other kinds of systems. And then the second part, I want to focus on a very specific set of issues, the sorts of things where I think you know, actually mathematical guarantees are really essential to get answers to problems in AI. So, okay, the first part of my presentation, I guess, is really a bit of a preview of my talk on Tuesday, and this slide, well, the next slide is borrowed from that. So it's all about you know, modeling AI systems and modeling the processes that produce them, understanding what's behind the performance of these AI models that have been so amazingly successful, and you know, with the hope, of course, that we can build better systems, make better use of resources, for instance, computing and data resources. But it really is taking a modeling approach and thinking about an engineered system as if we were modeling a biological system or a chemical process and so on. And you know, that's the way things are. This is a methodology that really was developed by practitioners through you know, hill climbing performance on benchmark problems, and this is where we are in the world of AI. One thing here that's been, you know, really exciting is there's actually a lot that's emerged from this empirical work that is surprising from the point of view of theory, of the classical optimization theory and mathematical statistics. So let me say a little bit about that, and you know, as I say, this is a slide from borrowed from the introduction of my talk on Tuesday. Okay, so when we think about a statistical learning problem, there are three key issues that we conventionally want to trade off. There's a representation issue of, you know, there's some relationship that I want to model, you know, and maybe that's predicting the next word in a language model, for instance. Maybe it's labeling an image. Is that relationship something that I can accurately approximate using the set of prediction rules that I've chosen? There's an optimization issue. I gather a large data set and I want to get a good fit to that training data. That involves you know, some sort of a choice of parameters. It's minimizing perhaps a loss defined over that data set. And then there's a statistical question, an estimation question of saying, well, you know, I don't really care to perform well on my finite training set. I'd actually like to have a model that performs well at deployment. So, you know, what do I need to guarantee that? And you know, classically, the answers to these questions have been from the approximation or representation side. We use very rich non-parametric families of functions that you know, can approximate things that satisfy, you know, rather weak conditions. On the optimization side, we lean on convexity, so we can come up with guarantees that algorithms will find very good near optimal solutions in a time that's, you know, scales very nicely with the accuracy of the solution and the scale of the problem. And we use nice stable implementation. So we think of the algorithms are typically set up so that they can be viewed as time discretizations of a nice convergent differential equation, for instance. On the statistical side, you know, we ensure that good performance on a training sample leads to good performance at deployment by explicitly controlling the statistical complexity of the functions that are chosen. So, you know, in these non-parametric classes, we might impose regularization or something of that sort. And then we use these tools like uniform convergence that say, you know, within a set of functions that have this statistical complexity that's suitably controlled. Sample averages converge uniformly to expectation. So good performance on a sample means good performance at deployment, of course, under this, under probabilistic assumptions about the process generating the training data and that carrying over to the setting at deployment time. So in modern machine learning, a lot of these things are really, really quite different, and you know, they raise a lot of really fascinating questions. On the approximation side, you know, maybe less so. There's the complexity there seems to be provided by depth or compositionality, and you know, maybe some other issues, some other approaches. There we go. That I won't talk about here. On the optimization side, you know, far from having convex optimization problems, we have these really, you know, quite ugly non-convex optimization problems. But in practice, it seems you can find very good solutions, provided that the number of parameters is very large. And Joan talked about some of the theory that's been developed in, for instance, the wide shallow nets case of the mean field theory. And, you know, far from having stable algorithms, the practitioners have found that, you know, instability seems to give much better performance in practice. And, you know, that's sort of fascinating. Far from the regime where we're typically pushed by modeling things as a approximation of a differential equation. On the statistical side, you know, there's very little explicit control of statistical complexity, and in fact, it's the properties of the algorithm that determine the properties of the solution that it finds, that determine the statistical properties of those prediction rules. So it's really these optimization and estimation questions are much more intertwined in these systems. And far from uniform convergence, we're in a setting where actually you get a fit to the data that's too good to be true, that you're fitting to noise, you know you're overfitting, and yet that overfitting doesn't seem to be hurting at prediction time. And that's really fascinating, a new statistical phenomenon there that's also seems to be, you know, has raised a lot of really interesting questions. And, you know, as Joan mentioned, we're far from this IID setting. You're really training with data that's very different from the setting at deployment time. So, you know, it's raised a whole lot of interesting, I guess there are a few of these that I'm going to talk about, some you know, small steps, some progress in understanding in my talk on Tuesday. But, you know, just at a high level, I think there are lots of really fascinating questions that have been raised by the practice of machine learning that, you know, really demand rigorous understanding. And I guess, okay, so that's the aspect of, you know, understanding, using mathematics for the science of machine learning, this technology that's behind AI. You could imagine answering many of these questions empirically, you know, treating this as an experimental science. And I guess the second thing that I wanted to focus on here is, you know, what are the important questions that really require mathematical solutions? And I'd like to raise, you know, one area here that's, I think, really important and, you know, a real opportunity, and that's the area of AI safety. Coming up with guarantees that the decisions that these systems make are correct, are safe, are good in some sense. And of course, you know, these are generative models. They're probabilistic in the choices that they make, and they're inherently unreliable. That's by design. So, you know, I think the right way to think of this sort of question is to think of systems that are composed of unreliable components, and yet we want the system to be performing well. Joan mentioned this sort of recent approach of AI agents that are used in a harness. You know, and the way to think of that, these are AI agents, okay, for mathematical reasoning, but also, you know, to perform a lot of tasks that we might think of as arising much more generally in modern office work. These are language models that are used, for instance, to, given a problem, to plan a path to a solution of the problem, to brainstorm different aspects of that, to reason about the steps to take, maybe to call external tools, go and do a web search for something, to try to do some formal verification of some piece, try to provide a critique of different aspects of the decisions that are being made, to debate things and so on. Each of these steps is a language model being used as a component of a much bigger system. And so, we certainly know that those components are all unreliable. They're generative models. But on the other hand, this is a feature of any complex engineered system. It's built up of components that we know are going to fail. You build a passenger jet, and every component of that jet has a limited lifetime, and yet, the chance of a catastrophic failure is really small. So this is the kind of direction I think that's really fascinating and really hasn't, has opened up a lot of really interesting mathematical questions. It's analogous to this pioneering work of John von Neumann more than 70 years ago. I don't know if you can read that. The title of his paper was, this was a Caltech talk, Probabilistic Logics and the Synthesis of Reliable Organisms from Unreliable Components. And the idea there was to develop a mathematical theory. The mathematics in this paper is really very simple. But wanting to treat errors in components in a rigorous way and come up with reliable systems. I guess the motivation at that time was the development of computing systems with very unreliable components, things, relays and valves and so on. And as the scale of those systems grows, that the components are going to be failing, and yet you want the system to do what you'd like it to do. So of course this led to this whole area of reliability engineering, guaranteeing that these failures of components is not going to lead to a catastrophic failure. But crucially, that depends on statistical independence of component failures, and that's just not the setting that we're in the LLM world, where these components are all very closely related. Anyway, I'll stop there. I think that raises lots of fascinating and hugely important questions that we might hope to answer with tools from theoretical computer science and mathematical statistics. So I think it's a really great opportunity and really very important. And I did want to flag a whole set of talks, and I apologize for the ones that I've omitted, but there's a lot of related work, for the rest of the Congress in various different areas that touch on the mathematics of AI. So I encourage you to go to those.
Thank you. Dean.
Well, thank you very much for the organizers to invite me here. So it's good to be back to the mathematics community. I was a math major, so and I went to statistics. So I think it's a great, my two colleagues gave very good overview. So I'm going to delve into some problems from the practice of AI, how mathematics can rise to be useful for after empirical work. So the title is Relevant Math Essential for AI when Combined with Empirical Work. Next, please. I do it.
Yes.
So I will just give you 3 vignettes, right, about 3 AI topics that are close to what my group work on, and leave with a question. The first is that we already heard that the pre-training is very important, mostly done in frontier models. They're open weight models. And the one people use now is called Gemma from Google. And they all kind of fall into the topic of AI capability development, right? Deep learning very much start from empirics, running a lot of GPUs and benchmarking. And then we start doing some relevant math, and usually it's only part of it, and we do more empirical work. Some of the lessons learned from math will be tested or guide the empirical, and so there's this whole iteration cycle. And the second topic is getting more important. Peter's already alluded to AI safety, right? We need AI governance. There's less and more interest now in AI governance, even in the US. And big part of making AI safe is actually making AI interpretable and in a reliable, trustworthy way, right? So you can see that this deep learning model is a little bit reminiscent of our own brain. I don't think neuroscience would agree that it's really like a brain, but it's getting very complex. A lot of the scientific methods in the high level is being used, like when we understand the human visual cortex, right? Many years ago, people did very simple stimuli, like you have bars, you have different like orientation. This famous work by Hubble and Wiesel to understand V1, which is the first visual cortex area, which is like wavelets, right? Edge detection. And similar kind of approach is being used here. We use very stylized mathematical models. I'll give you an example. And then we put into deep learning, even now very simple one, see how it works. So give some insight in the very simple setting, how deep learning might be working, right? So you can have stylized math model. I'll give you a case about modular addition. And then we try to understand it, and we see different phenomena, something called grokking. And then we understand, we try to make a little more complex stylized mathematical models, right? You see neuroscience, we have more and more complex with stimuli, try to stimulate the brain or print the brain. So there's a lot of parallelism between neuroscience development and how we try to understand AI. And trustworthy AI, reproducible AI, especially AI in science, is getting very important. We have a lot of now actually workflows for AI in science. I'm visiting Flatiron, and people are trying to do protein folding, all of that, right? It's really AI. It's being a lot in science, and we have developed something of a vertical data science, try to really look into irreproducibility or try to make things more reproducible and take into account more uncertainty sources. And there we also see we need math. So I want to leave with a question, probably will be picked up at the discussion session is, how do we keep enough human math intelligence while using AI for math? I know this panel is more math for AI in the sense of maybe traditional math, but most people work also using AI. So it's not separable anymore. And how much human intelligence in mathematics we should keep. So the first vignette I want to give is that we already heard about mean field theory. It's like when you have this infinite width, or the width n goes to infinity, we can see regularity. Use law of large numbers from probability or central limit theorem. And three very important parameters is like, how do you initialize pre-training the variance relative to the width? Use ID Gaussian, and also which algorithm, usually stochastic gradient descent, and there's this learning rate or step size. And if you set this parameter differently, you might get into the lazy regime, which is no feature learning. But newer work, which is related to mean field theory, but doesn't go quite far beyond that, it's called the MUP, Maximum Update Program regime. You set in a way that you make sure you have feature learning in the sense of your uniform stability. All these different quantities, actually when you progress, going further into the higher layers, stable. And one very important application of this has been using small model to figure out the learning rate. Because it's limiting result, then you can have a much better way to start the learning rate for huge models. So it's a huge saving in terms of efficiency. And most of us actually don't do pre-training, right? We take an open weight model and we do fine tuning. LoRa is low rank adaptive learning. It's very, very popular for fine tuning. So on the right, you see you start with a pre-trained weight matrix, everything together. And then you don't just do gradient descent on that because it can be expensive. What you do is that you try to add to it a product of two low rank matrices, B and A. And in the LoRa algorithm, people use the same learning rate to progress, right? To do low rank adjustment based on fine tuning data. The work we did is called LoRa Plus. It's use infinite width mathematics in some simple models and see that if you want learning, feature learning, and stability, then you should not set the two learning rate to be the same. You should actually set them differently. And the result is that you actually have 2 times speed up. just because you did the math and we verify with the best large model we could. And we also have a slight performance improvement because in some sense, you're traversing a different path in this huge dimensional space, right? Deep learning has a lot of good universal approximation probably, but anytime you're not searching for all possibilities, you start with very random features, basically, random weights. And then you use the data, a very small, like, path in the huge space guided by data. So I would call it like almost like algorithmic maximum likelihood. You use the data to find a parametric family whose space, which is low dimensional, and you try to stop early, right? So this is something very much, we came up with the idea of using different learning rate because it's infinite with mathematics. And not just that we wrote a paper actually including these two big code databases for fine tuning, and one is Llama Factory, one is Hugging Face. So I think infinite weight theory will continue to be useful for AI capability development and analysis, right? You go to the simulation, and right now it's law of large numbers, central theorem, but I would just add flat iron. Some interns are working on things to go to the next level, maybe getting some better, precise approximation. And as I mentioned, for AI governance, so all the regulation agencies need to look at this and like to understand why does it. If I'm a patient, a very sophisticated model give me a diagnosis or give me a treatment, I might want to know how did they make this decision. And people have been using sterilized generative models, as I alluded earlier. This is a very prominent case study from people in DeepMind and also my colleague in Berkeley. Something's a modular addition. Right, you have two integers, you have prime number 311, and the input data, you have all possibilities. You have A and B from 0 to 300, 100, and B from 0 to 11. And then you have C, which is A plus C mod 311. So you do one hot encoding, and you give very simple one layer transformer this data. And what they find, this is what kind of when I first heard it was kind of blown my mind away. And this very simple deep learning learned to go to the Fourier space. So the embedding matrix actually transform the whole input one hot coding into the Fourier space and use the cosine sine formulas basically to do the calculation, to do the addition, and carry the invariance in the circle. And they see there's something they call grokking. So grokking is that if you look at the blue curve, it quickly overfits. But if you look at the test, which is a red curve, it has this almost like discrete phases, and they characterize as memorization phase, circus learning phase, and cleaned up phase. Right? So this is very much empirically illustrated that you go to the Fourier space and use this very nice sine cosine formula to do the addition, and then you can generalize really well. But it hasn't been proven, actually we're working on it, to show mathematically this is what the algorithm does. And there are many like automata, other type of study model. We're going to first do empirical studies, and we need to prove that's what it does, right? So this is like you use all this simple style model, you understand what's going on, and you hope give some insight about the bigger model. And even going further into the practice of AI, right? AI for science is many universities, including Berkeley, going to search for AI for science faculty. But we actually in an AI reproducibility crisis, right? Science paper, Nature paper. And this is really nice and new. 15 years earlier, we had a replication crisis. This is just got multiplied because more people using data analysis, automated, and we have more irreproducibility. That means things cannot be replicated. And if you look at how data scientists, you can say make it bigger, which I'll show you, AI workflow, is that there are many, many, many steps when you develop a data science machine learning algorithm for hospitals or AI, now agentic, it's a system science. And humans make a lot of judgment calls, right? We decide what data we use. There are many databases, and we decide how data is cleaned. Actually, this is a huge source of uncertainty. I had a class we did. People can get very different results depending on how they clean the data. And then we have many, many choices for which algorithm you use. Now we have many models, how you devise a agentic workflow. when you have many, many human judgment calls, you often create irreproducibility. And irreproducibility will create distrust, right? So it makes people don't trust what we get, because if two groups of people work on the same data that have been paper written in social science, you get different conclusions about the science. It's not going to increase the trust in science. So we want to include this into the consideration formally. So we developed this framework for the last 10 years, the first paper 2020, and then the book came up 4 years later. There's a free version. So we really put machine learning and statistics together, called PCS, predictability, computability, and stability. So predictability in the book already expanded to reality check. Prediction is one way, but you can use other quality of domain knowledge to do reality check as well. And stability is an expansion of the traditional uncertainty and the probability model to reasonable human judgment calls, right? You need context. What's a reasonable judgment call? Usually the field has some sense, and we integrate and expand machine learning and statistics. So now let's go to AI workflow. This is Gemini generated. This is 18 steps, right? And I didn't give it, just I said, give me a AI workflow. Suppose for each step, right, you can see that data collection, if you have 2 choices, and data cleaning, you do choice, usually we have more. 2 to the power 18, you get 26,000 possibilities. It just quickly grow, and it's combinatorial. But experimental design come to rescue. This is my late colleague, Qing-Shui Chen's book, Factorial Design. Right, for this problem, if you use experimental design, if you only want to keep the main effect and pairwise interactions, you don't need to do 26,000 runs. You can do 20 runs. Right, so this is a huge saving for design space. Use orthogonality, resolution, and other properties. And the factorial design is really sits in the middle of mathematical statistics and combinatorics, coding theory, finite geometry. But now for AI, usually they know what they care about. But with foundation models, we want many, many, many things which are unknown at the development stage. So can we do design to accommodate more unknowns, at least the best we can, and also with efficiency? And this AI experimental design will include also benchmark design. A lot of the benchmark just made because somebody want to make it. One concept missing, which is very crucial for statistical inference, is actually representativeness, or something people call validity, right? So if you have benchmark, if some frontier model passes benchmark, what does it mean when it's being deployed in the wild? Which population and community will be happy, will be affected? So all of that, I think we need a much expanded understanding about the design space. And new mathematics might be needed in the area of combinatorics, coding theory, finite geometry, and mathematics. And I think integration of the 4 or more probably will be the most active and interesting area of research. So my last point is the question, right? So IEEE Spectrum just published this article called What It Means to Be a Mathematician When AI Does the Math. And they have this table called 3 Futures of AI in Mathematics. The first, AI is your assistant. The second, AI got the elevated position, which is a collaborator. And the third, AI, it's autonomous. So it's hard to predict the future, but I think in the near future, it's likely you're going to see a mixture of all 3, right? Depends on people's value, their training. But for the first 2, we still need to keep enough of math, right? What I talked to many of my postdocs and mathematician friends, the prompts, the interaction become very important. You don't get good results. So I should mention that my co-authors, Sophie and Nikhil, both tried to reproduce our Laura Plus paper, the math. So far, whatever the access we have, the AI couldn't do it because it's a very new research area. And there's not a lot. It's still a statistical machine. You need a lot of patenting to learn. And this mu-p is pretty new, right? Not too many papers, so it couldn't do it. So I think the frontier of statistics, mathematics, especially the new ones, we need human intelligence. But we're going to take advantage of AI. But do we want to keep enough of it, the mass intelligence, individually and collectively? What's enough and how? So here are my thoughts. I hope there'll be more thoughts in the discussion. For me, the process human doing math is valuable beyond getting the mathematical result or productivity, because the cognitive abilities obtained in the process enable rigorous reasoning and models problem solving in other areas and in life. I was a pure math major. I don't do a lot of pure math, but I think my brain was exercised very well. And so I can solve the problems I solve, right? And also I feel like I can go back to pure math more easily. The second point is that there's a real possibility of losing diversity of creative ideas and approaches if we all interact with the same 2 or 3 powerful AIs. And that's all harnessing thousands of years of human intelligence. So how can we keep enough diversity? There was a paper I handled, was not exactly math, but I think says something I worry about. So this people asked 10 people to name 10 famous people. I asked 10 AI to name 10 famous people. And the name collection is much narrower, like a third of the list humans produced. Right, same question. If I ask the AI, because they're very similar, trained on similar data. So that's some basis for my worry. And the third is that there's a real possibility of losing outside stimuli. Right? I feel like if I under myself as a scientist, a lot of my good ideas came from not just sitting at my table working on my computer. I'm exposed to other things, unexpected connections, and interacting with other people, doing science, or sometimes just take a walk, right? Maybe the tree, I don't know. So all of that, when you spend too much time, somebody I know who spent a lot of time using $200 AI, agree that this person works harder, more time, because they think they can more things done. So all of this, I think, diversity for any community, any species is crucial to keep. And how do we do that and take advantage of AI? Thank you.
All right. So first, thank you very much for the invitation and for having me. So before getting in, let me ask you by a show of hand, who knows what is a foundation model? Okay, 10-ish%. And who knows what is a world model? Okay, roughly the same people. Great. So the goal here is to really deep dive into those, give you some intuition, and show what are some open research questions that you can help on. So just to give you a concrete example, so at least you know what we are speaking about. Suppose I take a picture of this room right now, and I ask you what type of question do you want to answer from that picture. So if I ask a bunch of people, we don't have time now, but if I do, probably you will get different questions depending on who I ask. Maybe someone wants to count the number of people, someone wants to know who is wearing this type of shoes, who is on their phone. So you have a whole variety of questions that people will care about depending on their use case. And training a foundation model is really about figuring out the recipe to prepare a model to answer any question that you can throw at it. Okay, so that's really the main challenge, what people are trying to do, is to figure out what training recipe or to produce a model so that out of the box, it can answer the need of the billion of users that will download the weights and start to interact with it. Okay, so we speak about all those different questions that the model can answer as a downstream task. So a downstream task is one specific instance. For example, here for vision, it could be to do object segmentation or depth estimation. And here you just see a bunch of examples, but you can think of more and more and more, right? Maybe someone wants to figure out the species of the tree in the background, the cities the picture was taken. So this is really almost infinite space of downstream tasks. And you want your model to be ready to answer any of those out of the box. What you have at your disposition is a big collection of data. So typically, this data is very, very diverse. It may not be clean, it may be imbalanced. It's typically things you can scrape legally online, but it really can include a lot of things, including synthetic data. Okay, so you have this. You don't have associated labels to them. So, for example, you just have a picture of a dog. You don't know what is the species of the dog, or you don't even know what it is. You just collect images. And you have to combine that with a training objective so that you can produce this vision foundation model that will be able to answer all those questions. After training, so suppose you do this right, so you have this foundation model. You want to keep it frozen, you keep it, as it was trained. And then you can train a very, very simple, maybe a linear transformation of the features it outputs so that you can solve any of those downstream tasks, okay? Today, foundation models are not very strong. That's why we need LoRa fine-tuning, for example, that Bean spoke about. But if we make a better and better work, hopefully fine-tuning will go away. Maybe not this year, but soon. So this is really the goal of foundation model research. Okay, so this is what was the state of the art until now. I mean, still now in many tasks. Dyno v3, so it comes after v1, v2, v3. The only thing I want to mention about this is that it was derived by a lot of trial and error. People trying something with some intuition, detecting, okay, there is a failure case because they monitor some statistics of their embeddings. They see the trend is going in the wrong direction. They add an extra term to their loss and so on and so forth. So because of this, they end up with a ton of hyperparameters. And if you look at the performance, the key thing to know is that the numbers inside are the performance of the model, higher the better. What you see is that if you change some of those hyperparameters, the performance can go from very good, let's consider 70 to be quite good for this task, to near random, you see you get near zero performance. And it does not make a lot of sense. For example, you see in the second table, this number of layers you put in the projector head. 1 to 2 goes 61 to 62, so it seems a good trend. You go 2 to 3, you go to random performance, okay? And this is because those methods have been derived really in an ad hoc way with tons of terms that fight each other, and they are in a very, very weird equilibrium, which is annoying because now if you want to scale up your model or use different data, you have to recross-validate everything, and as you saw, you don't have the compute or time to do that. Okay, so the main question that you have to think about is if you want to produce a foundation model, what could be some conditions you can derive that those models must fulfill so that you get good performance on your downstream task? So the interesting question is, think about downstream tasks. You really have a big space of downstream tasks. First of all, how to define this space? Should it be, a weighted space? You have probabilities. Some tasks are more likely to appear than others, right? Some tasks are common to many of us. And so how to really model this space and be able to derive pre-training solution or training losses from characterizing that. If you're able to do this, it's great because then you can say, okay, which training loss will maximize the average case over all those downstream tasks? Or if you care a bit more about safety, like Peter mentioned, you can say, okay, which training loss will make sure that I have this much performance on, at least 99% of the downstream task. And being able to do this type of characterization is really what's needed to have better pre-training losses and better model overall. Okay. Right now, we don't know how to do this very nicely unless you do some very, very simple assumptions. So one thing we did is we said, okay, we want to be good on average across all the downstream tasks on average. When the head, so the way you probe your model is linear. So very, very constrained case, where in that case, I was able to come up with a closed form solution. The hope is that you open the paper, you see, okay, this is trivial, you know to do better, and then you come up with a V2 of the paper, and this improves the way we do foundation model. So that will be the ideal story. So if we do this simple case that I said, so we take the average, you obtain a loss function we derived in this paper. And I won't go over the detail in the interest of time, but the key thing is that now you have still a bunch of parameters, but you understand exactly what they do, and your loss is much more stable with respect to those hyperparameters. And this is very crucial because now when you speak to people who want to apply this type of loss, for example, on medical images or galaxy images or other type of tasks, they just want something that is reliable and work out of the box. They are not at Meta or any big companies. They cannot spend thousands of GPUs to recross-validate everything. And so here, because of this construction of this loss, you get something quite reliable. And because of this, it works out of the box, and therefore it can beat previous SOTA on a whole lot of benchmarks. Okay, so this was foundation model. Going to world models, you can think of it as a special case where now you have time axis in your data. And so you want to be able to model transition dynamics, for example, in robotics, understand what is the consequence of an action in the state of your robot and the state of the world. So still you keep the foundation model flavor, as in you want to be able to solve many things. You want to produce a world model that can be used to have your robot navigate the room, pick up something, empty the trash, fill your fridge, whatever is it that you want to do. So the way this looks typically is that way. So you have multiple observations. Again, you have the time axis. You will encode those observations into embeddings or features Z, and you want to be able to predict what will be the evolution of those features. Optionally, you have actions, which is this 80. So if you apply this action, of course, you also impact what the future will be. So you want to model that and condition your prediction on the actions. Okay, so this is, by the way, one flavor of world models called JEPA, which is not generative one. I would argue that generative models are not the right way to do foundation and world modeling. They are very specialized and not good on average. But yeah, this for maybe for the questions. So this is the way we do world modeling. Again, you want to make your prediction of the future correct. So you observe the future, you encode it, and you want to match that with your prediction. And you use the same loss as I described before to make sure that Z is able to solve many tasks post-training. So if you do this, you obtain this other version, so equivalent to the JEPA, but in world model version, which again is with only a few hyperparameters, very stable. You can apply it out of the box, and it gives you pretty nice performance, even compared to previous state-of-the-art there. So the key thing and the key takeaway is that those two papers I mentioned were obtained with very, very, very simple math. So we had this case where we want to maximize the average error on the downstream task. We obtain a characterization of what should be the distribution of the embeddings of Z. And then we do distribution matching to enforce this constraint. We do it by doing Kramer wall, which is a way to say, or to impose a constraint on a multivariate distribution. You can just do it on all of the 1D projections of it, and that's it. But this is done in a very trivial way. Okay, we just take the theorem, which is like 100-year-old as is, we apply it. There is a ton of things that could be improved with people who know about this area. So this is one thing I want to mention. Okay, so going back to what I said at the beginning, so there is a huge need to deep dive into those from pretty much every angle. It could be statistics and others. So for example, in this specific case, we use a statistical test as a training objective. So what does that even mean, right? To use a statistical test to train the parameters of your model. Can you still interpret the loss? Can you still interpret the value of the statistical test? So lots of very interesting questions. We do this in a high-dimensional space. So we do it via Kramer wall. We do this slicing. Again, is there a better way to do the slicing than just random uniform on the sphere? Is there some guarantees that you can get by doing a finite amount of slices? Because the theoretical result is with infinitely many slices. So all of those are completely open questions that no one even looked at, because no one used statistical tests for this purpose, right? So even with the very simple mathematical tools I know, which is basically bachelor level linear algebra, I was able to understand a couple of things. So, imagine if you start reading those papers, what you could do. And then, of course, you still have those old questions that have been here even before foundation model. What does it mean to be able to extrapolate in high dimension? Can you even produce a foundation model that out of the box, without fine-tuning, can solve most of the questions well? So all of those are very interesting questions that need to be looked at and answered. So of course, from this, you might wonder, okay, where to start? What is the best way to look into this? So the two papers I mentioned are a pretty good way to get started. So Le JEPA and Le World Model. They will give you a bit of background and intuition and the simple math we did there. In addition to that, there are those two additional papers that we put out recently. Again, they are very about getting some intuition and what will be some nice research questions to look at. So you can check those two as well. And then we also organize a bunch of workshops on world models, and we make sure that every workshop we record the lectures, and it's available for free on YouTube. So you can also check that to see a bunch of speakers speak about the latest and greatest of world modeling research and what are the still open research questions. So the first one you see was at the Flatiron Institute almost 2 years ago with a slight focus on neuroscience. We had the second one in Montreal in February, which was more for robotics. And then we have this last one in Chicago later in August this year. And there will be more every 6 months. So if you want to quickly see what are people speaking about, you can check those videos as well. And the very last thing I want to mention, this is something that was mentioned before as well, is that when you look at those problems, you really want to make sure they work and improve those models' performance in practice. Because it's very easy to fall into a trap to do some simplifications that lead to a result that does not transfer to practical improvements. And this is the key you want to always confirm. So you will need to do simplification, of course, but you want to do it in a way that the insight you get will transfer to improve empirical results. And so this is not easy because foundation model and world models are quite recent in terms of research areas. So you don't have a really clear ecosystem in terms of library. So if you want to get started very quickly, those are two libraries we maintain in the group that provide you key in hand, very, very well-tested libraries. You can trust the result. Things are reproducible. So going back again to the previous talk, everything is stored nicely, tons of tests. And if you want to work only on the loss, you can go there, change those 10 lines. If you want to work on the architecture, if you want to work on the data. So basically a library made for research. So feel free to try it out as well. And with this, thank you. And definitely look at this and feel free to send any questions if you have on JPAs and world models, because this is really the perfect time to get into this research area, especially if you have a math background. If you were pure, empiricist, even with a ton of GPUs, I would say, okay, it's a bit hard. You compete with a lot of the big labs. But if you come with math, you are pretty much in a community of 10 people. So really perfect time to join us. Thanks.
So if you notice, we were a little bit smiling up here because we can see the timer and we just finished in 1 hour sharp. So we are I'm very thankful for our panelists. So it's time for questions. There is a microphone here. So please go to the microphone and start asking your questions. They could be related to the talks that have been given, but also anything you wonder about AI and math in general. You can line up and then we'll answer as you go.
Hello. I would like to ask, how do you envision using category theory for AI research? Maybe specifically at what level of granularity you would use category theory?
Anybody wants to answer? Yeah, you can from here.
Yeah, I mean, it's true that this has already been done. So it's true that category theory is one instance of maybe a broader vision to use prior knowledge that you have about some learning problem, for example, symmetries or invariances, and these tools of invariance theory and category theory have been used in the past to let's say design architectures, neural network architectures that pre-encode this knowledge, like this mathematical knowledge. And it's an interesting open question. I think it's more right now up for debate to what extent putting this let's say hard-coded structure into the architecture is something that is going to survive the scaling laws, right? And we have seen some debates. Some people think, there's people on both sides of the spectrum that as you have more and more data, how much, whatever prior knowledge you have about symmetries is going to have smaller marginal, influence, right? And so I don't know, like Randall, that you maybe are closer to applications. You share this perspective or not?
Yeah. So for LLMs and vision, it might be a bit different. For vision, the state of the art really still rely on this concept of invariances and having a priori knowledge. As I mentioned before, suppose I take a picture here. What question you can ask probably is going to be the same question if I take the picture here or slightly translated or slightly rotated. And so you want to be invariant to this type of transformation. And so in vision, at least, it's something that people still use, and this improves performance a lot. In language, it's not used so much, but I don't know if it's because of the scaling law or because I don't know to provide good data augmentations, transformations for text. But yeah, this still plays a big part to have better pre-trained model.
And suppose that you have, you mentioned data. What if you have not only data as numbers or instances, but you have actual mathematical models already developed? For example, you have the several different models in fluid dynamics and data and so on, and you want to decide whether to use a stochastic method or a continuous model. So in that sense, how much do you think category theory would help in separating the style of reasoning over there?
Yes, it depends also what type of model you want to produce, because for one type of data, you might have a lot of prior about what invariances you want to capture or be invariant to. But if you use that too aggressively, it means your model will be very good only for this type of data and not so much for other type of data. So if you really care about having a foundation model, ideally you want to be good at everything. So you don't want to overbake too many priors that are too specific to a small subset of the task you will have to deal with. So maybe this can happen more at the fine-tuning stage, because then you only care about one task and one data set you are dealing with, and maybe not so much at the pre-training stage. So it's always a balance between being good overall versus very specialized, but only on a few subset of the task.
Thank you.
But characterizing that is a big research question. So yeah.
Thank you all for the interesting session. I work in an area of probability theory and complex analysis and applications of the AI, especially probability and complex analysis area, and apply it to the medical sciences. So one thing I find advantage in medical sciences is that, that you all covered many areas, but the accuracy is very important in medical sciences, testing the patients, and we cannot conclude a decision. We cannot give a decision to the patient which is not accurate, or you cannot say without any probability of having any chance of 50% chance, 80% chance. So the patients won't know whether to go with the treatment or not go with the treatment. So I work in the technology where we need to provide 100% accurate conclusions for for the patients in medical college. So I find the techniques in probability theory and the complex analysis very useful. And there is a technique called exact deep learning machines. So these machines provide the predictions with a probability 1. And they fit in only certain areas, not all areas, but wherever these configurations work, they provide with 100% accuracy. And just because the panel has not covered that particular area, and we recently tested for autism data in the US. As you know, there is a big debate in the US Congress also regarding autism, whether the vaccines are playing any role in autism. So we found that the models, exact deep learning machines, the prediction on autism is giving accurately closer to the reality, number one. And second thing, I agree with Bin Yu that the interface between the mathematics on AI and AI mathematics, that is very rapidly closing up. And then there is not much gap. The AI also thinking like a math, and mathematician also incorporating into AI. So my question is, giving this background, how about you think what the panel thinks about the accuracy in predicting the AI? Do you think it is important, or we can never reach the 100% accuracy, especially for medical patients or patients with those who need AI for medical treatment, like cancer detection or autism, cardiology?
I think maybe a quick comment. So yeah, I think depending on the specific application, so I worked a bit with neuroscientists for seizure prediction, and sometimes even the experts, when you look at the recordings, they are not sure if there is a seizure or not, and which stage of the seizure it is. And so some areas are so complicated that even experts disagree quite a lot. So for this case, where you have inherent uncertainty, it may be very hard to hope that a model can reach 100% accuracy, probably because the signal is just not there. So there might be also this thing, conflicting results. But
Yeah, I agree with you. I mean, for math, we need to eventually reach the practical solutions, useful solutions for the patients. And in the morning, also today morning, we heard that a numerical PD approximation where she showed the Dr. Buffa, she showed how to use the PDs for approximating the cardiology, the cardiology, nervous system, other things, whatever she showed in the morning. Thank you.
Anybody wants to add something?
Yeah, maybe I'll add something to that. I think a lot of time to get 100% accuracy, right? Work with ER doctor from UCSF. And for bleeding detection, say brain injury, you can achieve 100% accuracy if you send all the kids to CT scan. But CT scan has radiation, and that will have a long-term cancer risk. So I think accuracy is not the only thing under consideration. You usually have to do a trade-off. So there they try to 99%, and that's of course call. So usually in real situation, there are multiple measures of performance or metric 1, 2, and often you have to like have a trade-off. And also as Randall said, doctors also differ for some like vague diagnosis. Here you actually can be 100%, you just send every kid to CT scan. But of course, small bleeding, you might still miss that too, right? So it's kind of hard. For me, it's like never probably 100%, but can you get as high as you can, and while taking into account other considerations.
Thank you.
Thank you.
Thank you, panel. Professor Bartlett, you mentioned that the behavior of modern machine learning methods is mathematically surprising, at least sometimes. The use of infinite width in neural networking theories already use non-Archimedean ultra powers, such as a countable copy of the reals modulo a non-principal ultra filter on that countable set. But that is as transferred extensions of real analysis. Could some of the surprising behavior reflect the restriction of learning theory to essentially Archimedean geometry rather than the use of intrinsically non-Archimedean or adelic structures in mathematics?
Maybe. Yeah. I don't know. I mean, this would be an interesting direction. I mean, I guess I was giving a broad description of a bunch of surprising kind of empirical observations that are not consistent with the kind of wisdom that follows from the mathematical statistics and learning theory that we've been developing over decades. So on the generalization axis, there are analogous kinds of surprises that have arisen in optimization in the properties of those things. But I'm not familiar with the difference that might arise by exploring that direction. But it sounds like you might be interested in exploring it yourself, and I'd encourage that.
Thank you.
So my main research areas includes constructive algebraic structures, and constructive calculus of relations. My question to you is, what is your opinion about the role of constructive mathematics, that is, mathematics performed within or by intuitionistic logic in your areas of expertise and in general in artificial intelligence?
I didn't understand. Could you repeat the question? Sorry, there was a sentence I didn't understand.
Okay. My question is constructive mathematics, defined as mathematics performed by intuitionistic logic as a background. Its role in the areas of your expertise, and in particular, and in artificial intelligence in general.
I guess because my ignorance, I don't know. Like, can you explain a bit what's constructive mathematics?
Constructive mathematics is mathematics which use intuitionistic logic instead of classical logic.
Instead of
Classical logic.
classical logic. I don't know.
Not that I'm aware of.
Artificial
Yeah.
mathematics.
We haven't come across that.
Yeah, it seems that this might be a bit far from the ideas, but it's still, I mean, as Peter was saying before, I mean, all connections are worth like thinking about. So
Sorry, we don't. You have to go to the microphone. We don't hear otherwise. Whoever was talking. Sorry.
Hello. Yesterday, we learned at the Simon's reception that it's a clever strategy to surround yourself with the smartest people you can find. What do you think in the future it will change to surround yourself with the smartest agent you can find?
Maybe just a little parenthesis. So I don't know if everybody was at the reception last night, and in the video that we watched of about Jim Simon says that the best thing to do is to surround yourself with the smartest possible people. So the question is, smartest possible agents.
Smartest possible agents you can afford.
Afford, exactly.
I think already today, especially if you do academic research, there is a huge benefit of finding the smartest adjunct, which does not mean they are smart today, but smartest among not very smart is still better than nothing. And there is a huge help, especially to help you review, for example, experiments, make sure things are reproducible, finding edge cases, and so on. So there is already a huge benefit today, but I did not find one that was replacing my colleagues yet.
I think if I have all the money, I still want to surround myself with half smart agents and half smart human beings. I wouldn't go 100% agent, just not my choice.
Okay, thank you.
Want to add anything to you guys?
I'm with Ben here.
Yeah.
Hi, my question is, during the talks, you mentioned a bit lack of some parts of mathematics, say related to central limit theorems or similar things, and I observed the same thing. Many advanced mathematics seems to be missing for, say, machine learning and AI. Why is this, and is there any specific mathematical reason that hinders those developments? Say, for central limit theorems, you have a lot of void, even for transformers. I think that Professor Rigolin now has one article on this, but all of this is missing. I relate briefly also to earlier remark about constructive mathematics. I think it relates to computer mathematics, and it's another question, how to maybe include specific non-statistical, probably nature of machine learning algorithms using computer mathematics and advanced mathematics in future research. Thank you.
I think, I think for the mathematics, for the first part of your question, it's very interesting because I don't have a strong mathematical background. But if you find the area where you can simplify things, get results, but those results transfer to actual models, this is a type of mathematics that people really need today. More abstract things could be useful within 3 years, I don't know, in the future. But today, people really want mathematics that will help them reduce the search space, like being said. And this already restricts a lot the whole space because you need people who can also implement things, validate things, and make sure that what they derive, or they have a sense that what they derive is a simplification, but that it will transfer to the real world. And I think this is something that maybe people don't exercise enough, or there is not enough events like this one to try to motivate people to try it. So that could be one reason. It's just not enough people trying it to start with.
Yes, go ahead.
Maybe to add on Randall's point, I might have the the perspective that the mathematics of AI is very similar in spirit to applied math, right? Where it's kind of everything is grounded on something that you observe from the world, some experiment, then the mathematics that you need in a sense are determined by the experiment itself. And in some sense, the math that we are using today to understand AI is the one that it's the best we have found so far that is adapted to what we have been observing. Obviously, we don't understand everything, right? And there might be even new math that we need to invent, right, to understand some of the mysteries that maybe Peter is going to talk about in his plenary talk. So I think I view it more as an opportunity to to discover maybe new math, but they're all grounded on the experiments that we are running.
So I think if you look at the human community, right, it's the first time I ever came to ICM. I did, something about the virtual 2022. So I think a lot of new mathematics, even the existing mathematics, could be useful, but maybe the people in AI, machine learning, don't know.
Yeah.
Right. We have separate departments, and just a lot of new things. I mean, I didn't know what was constructed mathematics, to be honest. Right. So I think this need to be, maybe the mathematicians can write more like tutorial paper to make it very accessible, some structure, and then have the communication with the machine learning. I just want to put in a plug for Simon's Institute, but Peter and I are affiliated with it. And we have a lot of machine learning and large, and the LMM type of workshops, right? That's one like stop for people coming from mathematics and see what machine learning AI people are doing. So we need all of these like meeting points so that, and we also need translators to translate something to a level that I can understand, right? Just impossible for me. Maybe I do a lot of learning mathematics now through Gemini or ChatGPT, but I don't know whether, I think it's okay at my level, right, for a lot of the new mathematics. So I think the communication and then make things accessible from both sides will really help so that we can take advantage of all the mathematics developed recently, which people like me probably not aware of.
Yeah.
Thank you.
Okay. Thank you. Thank you. So before I ask the questions, let me introduce myself. I graduated from Berkeley. I didn't stay in the academia. I went to Wall Street and Silicon Valley. So my questions were based on some industrial problems. Thank you. The first question is about a fundamental question about AI. I want to ask you, is hallucination an intrinsic value or property of AI? I try to give a proof that hallucination is an intrinsic property of AI based on measure theory. Do you think hallucination is an intrinsic property or not?
Yeah, I don't know if you can extrapolate in those high-dimensional spaces without hallucinating time to time. So it might be that you must have some form of hallucination, which itself if you look at humans, some people call it, creativity or simple mistakes. So I don't know if even us are immune to hallucination, but yeah, maybe you have a...
Yeah, I mean, just to relate this to the earlier question about medical decision making, uncertainty quantification, I think, is a really important direction. And if you think about what large language models are doing, what they're trained to do is model a big mixture distribution. Given the text up to this point, what's the conditional distribution following that? And that's, that mixture distribution may have some low measure parts, of course, and you call some of those facts and you call some of those hallucinations, but you're modeling that distribution even perhaps accurately, and still hallucination is an accurate model in the sense of a close approximation to that conditional distribution. On the other hand, what you really want is to have a calibrated probability, to a calibrated output, so you know about the uncertainty that's associated with a given prediction. This is a really important direction.
Yes, and let me continue our question, because we discussed about the traditional statistical method for training. But when I was at the industry and in Wall Street, I believe that there will be something beyond statistics. For example, if we want to train something with some predefined label, let me just give you one example. Before Columbus discovered America, Columbus, he originally believed that he wanted to discover a route to India. Okay, so for example, if currently we are using all of the knowledge pre-labeled at this stage, imagine we want to discover America with AI, but we train the AI with all labels about India. The reason was that at that point, the Europe people didn't know about America. They didn't have this tag. So if we are using some statistical way to train our model, and if we manually define something about hallucination, then in the Columbus stage, if he discovered something called India, we say, okay, it's right. The reason was that we have no label about America.
Okay, sorry, what's the question then?
So the question was that I first asked...
Briefly, because we want to give a chance to
sorry, one last question. I first asked, is hallucination an intrinsic value or intrinsic property of AI? Because humans make errors, we will have hallucinations. My second question, I give an example of Columbus to ask if we want to pre-label all those data, and based on our current knowledge, we will have hallucinations. Okay, what do you think?
And I think in your example, if you have like a world model and you try to plan to navigate to India, and then you end up in America, which could be for many factors, maybe you have the wrong knowledge, or maybe there are external factors that change your plan, and then you have updated facts. I think the research question is how to quickly ingest those updated facts into your model without forgetting anything else. So this quick adaptation is one big research area that people don't know how to do, but yeah, you need exploration and maybe random exploration in the real world as well. I don't know if that answers the question. But...
Thank you. But sorry, one last
I'm
question.
sorry. I think we have to
no.
give. Thank you. We have to give a chance to other people who are lining up.
Thank you, everyone. I think AI will be better than mathematicians at doing math within 2 years. I didn't say that. That was said by Mr. Jacob Zimmerman, who was here yesterday. He also stated that he has stopped accepting graduate students in math because I don't want to train students for a career in mathematics that may no longer exist. So I want to hear your comments about that. If you are professors, are you going to accept graduate students? And what are your advices for students who are currently like college students or maybe upperclassmen of high school or maybe even already graduate student that are already studying math? Are their lives doomed? Thank you.
Yeah.
I am taking students whenever NSF is willing to give us some more funding. So, you know, yeah. So, I mean, I'm not claiming to have any, lens into the future and what the future is gonna be, especially, 2 years time in this world now it's a lot. But I think I don't know, this might sound naive, but my take on that is that as long as there is curiosity and human curiosity, there will be a need for us to train students, and I think we are still gonna. I think there's still so many things that we don't understand, and still like a lot of curiosity and a lot of shared sense that we want to understand it together. And I think my perspective is that the community uh, is still there, and there's still, I think, momentum to try to keep going and keep thinking about these questions. And who we'll see what the future brings us. But I think at the moment there's still a lot of critical importance of having humans right in this objective, in this journey.
Yeah.
I think just to add something, in my case, I would rather get people who did math, because this gives a huge amount of intuition and way to think about the problem. So even if now they won't spend as much time doing math and they will do more experiments, they will just be so much more efficient because they will already get intuition of what makes sense and what does not make sense, that they will be very productive graduate students. And even if you don't know math, I think it's useful to learn math, even though it's math that ChatGPT can do today, just because it gives you some intuition that otherwise you don't have, and then you will just waste your time trying a whole lot of things for nothing. So yes, there is still a huge value, just maybe for a slightly different purpose, but still a huge value.
Anybody wants to add more?
Yeah, I mean, I think these are hugely powerful tools, and they're getting more powerful every day, and we should be making the best use of them that we can. And I think of course it's hard to predict the future and where they will go, but while we're playing a role, we should be taking advantage of these tools.
So I would think that math is still very useful for critical thinking and rigorous thinking, but even for a statistical paper, I tell my student that they can use summarization paper half of the time and the other half time without knowing what's a better proportion. Still read the paper in the old-fashioned way and summarize it. So until we figure out better how much, I do think that going some things through your own brain is different to exercise your brain than just use agent and become outsourcing all the mathematical kind of techniques to. But things might tell me something different. But right now, that's what, and definitely I'm taking students, and but I think a lot is really learning how to learn, learning how to do research, not the particular productivity. That's never been my emphasis in my training. It's really have the skills so that they can face new problems. So for that, I don't feel at this moment threatened for that type of advising.
Thank you very much. That sounds encouraging.
Thank you.
Maybe add some, I don't know anything about AI, but I want to add that I feel like at this moment, we are just using all the experience that we all have up to this moment. So if we stop having graduate student or we stop learning or whatever, like, I don't know, in 20 years time,
who's going to
verify?
Sure
if people know how to ask questions. So that's my...
Yeah, that was my last question, like how much? I think
Right.
we probably can definitely use AI help a lot of things, but I think we need enough human intelligence. It's what I don't know is like how much, like numbers and things like that. But we probably figure it out.
Thank you.
Go ahead, next person.
Hello, thank you for the panel. I was an undergraduate math major, then I went into AI safety research. Now I'm a reporter. And something I noticed in this transition is how little math actually has been helpful thus far in understanding how AI works. Like one of our best tools for understanding the internals of how a AI large language model is computing something is a linear probe, like just a linear function. And I was struck by the thing about the like optimization wisdom has been less relevant. And so I kind of wanted to push against maybe the premise of the panel and get kind of opinion from the panelists on how useful should mathematics be to understanding AI, especially as like AI models continue to change very rapidly. Like, will human understanding keep up, do you think?
So one comment is I know what you mean by the linear probe. That's how we do AI safety right now. But I would bet that we have to go more complex than linear, right? Just what it is, and the data set is very small, very high dimensional. So this is just where we are, and linear models still very useful, right? But when we understand things better and better, I'll be very surprised that linear is enough. That's just my bet. So the other thing is not really the particular theorem you learn, math class would be direct useful. As I said, it's really, what's rigor, what's it's logically consistent. Those things, I think from this phase, a lot is more useful than the particular can prove A plus, equals something. But the question becomes how much we should get people trained, maybe get into science, right? Get into other things, interpersonal skills, right? There are many, many other dimensions. I do think mathematics as a community need to go. I mean, we went there already in statistics, right? If you want to be a good applied statistician, you cannot just do math. You have to interact with the clients, the clinicians, and a lot of how you can work with them is about communication. It's whether you can explain things so they understand, and there are things you understand. So I do think that mathematical education needs to go beyond the math to multi-dimensional skills. I mean, you became a reporter, right? So apparently you had other things than just doing the math.
I mean, to clarify, it's like mathematical methods to understand the AI system rather than expertise build. Sorry.
Yeah, I mean, we're trying. So
yeah.
Yeah, I mean, if I might add, I think maybe it's already kind of indirectly in your question, right? But one could see that the role of mathematics in AI could be either something just that the objective is to describe the system, through theorems and maybe through simplifications that kind of capture the essence, versus to prescribe, right? To have, okay, here I understood really how it works, therefore I can make it better, right? More efficient or whatever. And I think it's important not to put the bar, we always get this kind of criticism, right? So that theory is permanently lagging behind practice in AI, and in some sense, what could argue that most of the advances in the field have been driven by empirics, right? By just people trying many things and then just, building on the experiment that really seem to show some understanding. But I think there's also instances where math has been, in some sense, the essential ingredient, right, in building something. And I want to bring back, for example, diffusion models, right, that are now, the gold standard to generate complicated structures, right? And there I can see like a much closer link between the algorithm and the math. But it's the point, I think it's well taken, right? That there's always this like increasing gap between practice and theory, and I think we have to live with that, right? And the same way that in physics, right, there's many experiments in nature, right, that we still don't understand, right? And they have been happening for millions of years, right? And so we still have time to catch up.
And just like those areas, I don't think we should throw our hands up and say, we'll never get that rigorous understanding. And I'm optimistic. We make small steps all the time.
Yeah, I think just to finish, I will say at least in foundation model self-supervised learning, There are some things you can do very nicely with math. So there are some objectives that you can prove those are not good ones to use, and some are strictly better, for example. So at least they serve to reduce the search space, your cross-validation space. But of course, you don't have like a single result that explains the whole thing at once. But there are a lot of very powerful isolated results that each of them cuts your grid search by like 2 per dimension, which becomes a huge gain at the end, like being explained. So there is a huge use case still.
Thank you for all your responses.
Hi, thanks for the panel. I'm a fourth year PhD at Yale Statistics. My name is Garrett Wen. So after the panel, I think I have several questions. Firstly, I want to ask, is the scaling law in pre-training stage of a large language model still mostly an empirical law, or is there a satisfying theory now? And secondly, as in the wonderful talk, I learned that mathematics is very powerful at interpreting and understanding the large language model and guiding the design optimizer, for example, the LoRa Plus. But I have a question. So is mathematics be able to guide us a new design of machine learning architecture, or is it important to use mathematics to design new architecture in modern large language model? And thirdly, in my understanding, I think we have 3 building blocks in machine learning, like data optimization and the model architecture. So what do you think is the most important aspect for mathematician to work on? Or should we just work on a unifying theory for all those things? Thanks. Yeah.
So I think from my expertise, the training loss is the key thing. So what we found is that if you have the right training objective, you still need some constraint of the architecture, but it does not have to be a transformer per se, can be others as well. But the training objective is really the key thing, at least in vision foundation model, is really the key thing that brings performance, and that is very interesting to look at.
Okay.
I didn't actually catch the first question. I don't know if others did.
So my first question is that is the scaling law in pre-training stage of ALM still mostly an empirical law, or is there already a theory about it? Yeah.
So there are simpler settings where the scaling laws are well understood. You can derive the relationship between the amount of data, the number of parameters, and the loss that you'll see, the predictive accuracy that you'll see. But that's in simplified settings where that make the analysis tractable. I think for the sorts of real models that are used in practice, that's not the case. It's an empirical kind of a phenomenon.
Yes, thanks.
So what's missing in the scaling law is actually data quality. Right, that's what a lot of actually the frontiers are going after, is the quality of data. They only has the size, right? It's really missing. So for me, for practice, it's still empirical.
I see. Thanks. Yeah. So what do you think is the most important aspect for mathematician to work on, like model optimization or data? So yeah, like you just said, data is important for theory for mathematician to work out the theory of scaling law. Yeah, thanks.
It depends on what's your skill set, right? You have, I don't know, a few thousand mathematicians. You're not just one entity. So a lot is really what's the opportunity you have, what the resource you have. So the question is, it all depends, right? Depends on whether you can make a difference. There are many problems. Architecture, I think, is a very open area. If you want really something, you can try, but there's not a lot of work either. So I think it's a combination of opportunity and your skill set. So I wouldn't know what's the most important thing, because machine learning institution and AI, very empirical, more engineering field. It's very different from like mathematics. You have these big conjectures and people work on. It's not like that, right? We don't have such things, and there's just many teams working on very important problems. You can ask a set of problems, but that's will be more appropriate for this area.
Okay, thanks. Yeah, thanks.
Thank you for the panels. I'm Joan from Posttech. You've talked a lot about that AI as a tool, a collaborator, and eventually perhaps an autonomous agent. If mathematics is increasingly use the same foundation models and AI agent, do you think this could make mathematical research more homogeneous? And if so, how can we preserve diversity in the way mathematical ideas are generated?
I kind of hinted in my comments, right? I think that's why you need to keep the human connection. You need a connection with the physical world and just ordinary people. I think there's a lot of things we don't understand how human intelligence work, but then take advantage. I'm like doing 50-50 type of thing. I think that's the only hope because we don't really understand how human intelligence has evolved. And I do worry about losing of diversity. So make sure you do see your friends. Don't just, 5 agents, 100 agents, you just become a slave to the agent to babysit. That's what I think happening to some programmers, right? They can now, I have a student work for a startup. Now the company he can also set things up on his phone to run the agents in the startup, right? I hope he resists just always programming things even now he's at home. So you need discipline. I have a friend who is now working for OpenAI. He tells me that he actually has 4 hours. He stay away from agents and he does it the old-fashioned way. So I think that's a good example. He's at OpenAI, but he's taking 4 hours a day to be away.
Okay, thanks.
Thank you for the great talk. I have a kind of personal question, but I had to ask this question. First, I'm a third-year undergraduate student in post-tech, majoring in computer science and pursuing a second major in mathematics. I'll be also studying at UC Berkeley as a visiting student this fall, and my main research interest is AI. I chose mathematics partly because I enjoy it, but also because I hoped it would help with my research. However, I found that many undergraduate mathematics courses are deep and fascinating, but difficult to apply directly to current AI research. At the same time, while I'm taking many other lectures like this one, I've seen cases where genuinely advanced mathematics seems to play an essential role in many difficult problems in AI. So even when I could not fully understand the mathematics itself, I could still see that it was doing something important. So that makes me hesitant to give up on studying advanced mathematics too early. So my question is, for someone in my position, would you recommend continuing to study mathematics broadly and deeply, even without an immediate application? Or would it be better to learn mathematics in a more problem-driven way when a specific research questions requires it? How would you decide between these two approaches? Thank you.
I think it can be very personal depending on your style. I know I don't have a lot of background in mathematics, so typically I find something very interesting and I start looking at it, and then this opens up areas that I don't understand. Then I learn it, I deep dive in it to try to solve this problem. So it's sort of hand in hand together, but maybe if you have a much better mathematical background because you learned it a priori, you don't need to do this process. So yeah, maybe it depends on everyone background.
I don't know whether you just take classes, right? For me, I don't like classes. So, I mean, try to learn things on your own, right? You can get deep into it, but try to be more self-motivated than just follow the classes. I think even the same topics, you can maybe ChatGPT at that level can help and be interact, ask critical questions. So I think to get into deep mathematics is useful, but you don't have to follow the class kind of format with all the available resources.
Unless that works for you. For some people, that's the great way to learn those things. And of course, you develop all the critical thinking and analytical skills from doing that, even if that it doesn't end up being the direction you pursue. So yeah, it's very much a personal question, I guess.
Maybe I would like to add one thing. I think that usually what I have seen for myself and other people, that new idea come from combined things that were not predictable. So, if you want to have something really new, it's because you might have heard something in a different area that you find the connection you bring in the new area and you get the new result. So I'm all in favor of learning about different topics in whatever way, via class, via reading a book or whatever, or asking questions to ChatGPT, I don't know, but yes, broad, I think it's good too.
But at some point you won't have classes, right? So,
exactly.
So eventually you will have to.
By yourself.
Yeah, but maybe undergraduate, that's how you want to do it.
I think we have time for a couple more questions. No, not for you, sorry.
Oh yeah, I was just about to say thank you.
Thank you.
That's very sweet.
Thank you. Yes, there is a lot of serendipity in mathematics and in science, and it's very interesting to hear such questions and to help students to find their way. Thank you for the panel, and it raises me very question as I'm working in discernment in the age of AI, and I will relate it to mathematics. In mathematics, we usually demand that the theorem come with its hypothesis. Do current theories of why the models of AI succeed come with hypotheses sharp enough to predict failures, or only with post hoc explanations? Behind my question, there is this idea that a theory with no predictive power over its own boundaries is closer to a narrative than to a theory. So we should require whatever explains the success of a model also predicts where and how it fails.
Yes, I think it's very interesting because you have, of course, a lot of assumptions or requirements that allow to derive things in closed form. But what people have found is that even if you go a bit away from those, it does not mean that the result or the ID will fail necessarily. So deep nets are quite resilient to this shift that you have between what you put in the theory and what happens in practice. Not for everything, but yeah, typically it's not because you break one assumption that suddenly nothing works anymore.
Yeah. And just to add on Randall's point, I will bring again the analogy with physics, right? Is that we can build theories and then as opposed to someone working on cosmology that needs to run a very expensive experiment here, to some extent we have the luxury that we can just test our theories much more easily, right? That we can just run the experiment and just see what happens. And I think we have seen in the community we have seen this kind of like virtuous circle, right? Where many of the theory has progressed actually quite quickly, precisely because we have been able to validate the theory through experiments, right? And I think this is one of the benefits that we have in the field.
Okay.
Thank you.
Hello, I'm Abdullah. I'm a third year PhD student working on math foundations for machine learning at the University of Maryland. My question is that a lot of the math that we do as mathematicians in any area usually is founded upon years and decades of formalization of mathematical ideas. And we usually build upon them. And though that formalization helps us state problems in a very precise manner and helps work on them. In my experience, a lot of the problems in machine learning and AI, the mathematical problems even, are not very easily formulated in precise statements. And a lot of the mathematicians that do end up working in ML usually approach it in that formal lens and usually end up proving results with too many assumptions that might not translate to real world implications. So do you think there is room for formalizing a theory of machine learning, or is it just a fact that that mathematicians will have to sort of work like physicists when dealing with problems in machine learning, where experiments will eventually guide us where to dedicate our efforts mathematically?
I think it's a mix of both. I think it is important to, so the first steps you take are always going to be under simplifying assumptions that, make the analysis easier. Many times you can extend those things and weaken assumptions, but the sorts of systems that are used in practice, I think, it makes no sense to try to formally model everything. So, there is an aspect that's modeling a simplified version of the world. But of course, then there's the to and fro of, okay, you have the information you get from that, and then there are further experiments that suggests, and so on. So I think a combination of both of those is a very informative way to learn more about what's behind, for instance, the successes of these models.
So the way the mathematics have been used is kind of reminiscent to how mathematics has been used in science, right? So I was reading a book in physiology or something, and it's like New York subway is not really laid out as really geographically. It started with the London subway, but it tracked enough useful features for us to be useful, right? So I think, but AI does move a lot faster than in biology, right? The Drosophila doesn't really change, in front of our eyes. So the speed does pose more challenge, but intrinsically, the nature is very similar how mathematics have been done in science and biology, which you need some formulation. You also have to do simplification, and things will evolve. But the speed is faster, for sure. So not too new to me, how mathematics is used.
We're going to take one more question because
Thank you.
I'm sure the panelists are tired.
Yeah, thank you for the great panel and for the very timely topic, of course, that you picked for this afternoon. Mathematics has obviously been a great tool to explore and understand science and has helped us. And there are many examples that were already mentioned earlier, like physics, where it has helped us a lot. Not so much in the field of biology, I would argue, and maybe particularly if you think about neuroscience and understanding the brain, I think we're still struggling, and it has perplexed us in many ways. So I'm using the brain for the obvious reasons that there is analogy to in understanding a large language model and the experiments you want to do there. So if we haven't found any good methods for brain research yet for decades, can we hope, or is it futile to try understanding large language models in the same way? And do we still need to maybe develop more mathematical tools or new mathematical tools before we can hope to get there?
I think in this example, like lobotomies are maybe more acceptable in language models than in brains, right? So maybe, again, that's one of the advantages that we have in our field, right? That maybe it's easier to validate the assumptions and the hypotheses than it is in some of the natural sciences. But I think your analogy, I think, is also correct, right? That as we try to analyze the system in its globality as a whole, as like a biological organism, the system just becomes so complex, right? That is the task of having an accurate mathematical description. It's just much harder, right? And so I think we have to share, we have to live with that, right? That I don't think there's any shortcut.
Anybody else wants to add?
8 seconds.
6 seconds. Well,
All right,
I
thank you.
think this was a good ending. Thank you to everybody for staying this long, and thank you to the panelists.
Thanks.
So how long are you here?